Our world is just humming with signals that seem completely random. I mean, think about the stock market or the data pouring into a self-driving car. It all looks like pure, unpredictable chaos. But what if it's not? What if there's a hidden order in there and we just need to learn how to see it? So that's the big question, right? How do we actually go about taming all this randomness? What mathematical tools can we use to not just describe the chaos, but to actually get a glimpse of what it might do next? Well, that's exactly what we're going to unpack right now. The entire science of understanding these random signals, it really all boils down to one single, powerful idea. It's called a stochastic process, and it is our launchpad for finding all that hidden structure. Okay, so first things first. Before we can even dream of predicting the future, we need a language, right? A mathematical way to model a random signal as it changes from one moment to the next. So what is a stochastic process? Well, think of it like this. If you're watching a stock price, the price at 9:31 a.m. is one random variable. The price a minute later, at 9:32, that's a whole new random variable. And so on and so on. It's really just a sequence of random variables, one for each tick of the clock. It's our fundamental tool for capturing a signal that evolves with uncertainty. Now, here's where it gets kind of wild. To perfectly, completely describe a signal, you'd need to know the joint probability of its value at every single possible combination of times. I mean, just think about that for a second. It's impossible. So we have to be clever. We need shortcuts to find the signal's most important features. Its hidden blueprint. Okay, so if a perfect, complete description is off the table, what do we do? How do we find that blueprint? Well, this leads us to two incredibly powerful ways to deconstruct a random signal and see what it's really made of. You can think about it like a signal has two different secret blueprints. The first one, using something called principal component analysis, is like getting the recipe, finding the core ingredients. The other, the power spectral density, is totally different. It's like seeing the signal's unique energy signature, its hum across all the different frequencies. Let's start with PCA. This method is all about efficiency. It takes a really messy, complicated signal and asks a simple question. What are the absolute most essential patterns that make this thing tick? By finding these dominant patterns, and the math nerds call these eigenvectors, we can build a much cleaner, simpler version of the original signal. We keep what matters and we throw out the junk. Now, the power spectral density, it tells a completely different story. It shows us where the signal's energy, its power, is hiding out in the frequency domain. Take white noise, for example. Its PSD is totally flat. The energy is just smeared evenly across every frequency. But a clean musical note, bam, you'd see a sharp spike in the PSD right at that one specific frequency. So the takeaway here is that the shape of the PSD tells you a ton about the signal's inner structure. All right, so we've got tools to model a signal, and we have tools to analyze its hidden structure. So now for the million-dollar question, right? Can we actually predict what it's going to do next? The secret to making the best possible prediction comes from this really cool idea called the orthogonality principle. I know it sounds super complicated, but the intuition behind it is actually beautiful. Just imagine you're standing in a room, a few feet from a wall. What's the shortest possible path to that wall? Well, it's a straight line that hits the wall at a perfect 90-degree angle. It's orthogonal. In prediction, that wall represents all your past data, and the shortest path, that's your smallest possible error. And this orthogonality principle isn't just some abstract theory. No, it gives us a concrete recipe, a set of instructions called the Ewell-Walker equations. When you solve these equations, they spit out the magic numbers, the coefficients, that let you build the absolute best linear predictor you can, all based on what the signal has done in the past. But let's be real. How do we find these magic numbers in the real world, especially for really complex systems? Nobody's solving these equations by hand with a pencil and paper. Instead, we build algorithms that can learn them all on their own. To get an algorithm to learn, you first have to give it a map. You have to show it what good and bad look like. This math is called a loss function. The best way to think about it is like a landscape with mountains and valleys. The high mountains are terrible predictions with huge errors. And the lowest, deepest valley, that's the sweet spot. That's the perfect prediction with zero error. The algorithm's entire job is just to find that valley. So how does it find the valley? It uses this brilliant little method called gradient descent. Imagine you're standing on that foggy mountain. You can't see the bottom, but you can feel which direction is downhill right where you're standing.
That steepness, that's the gradient. So you take one small step in that steepest downhill direction. Then you stop, feel around again, and take another step. You just repeat that process over and over, and eventually you're guaranteed to find your way to the bottom, to the point of minimum error. Now, as you can probably guess, there are a few different ways to hike down this mountain. You could use just one piece of data at a time to decide your next step. That's called stochastic gradient descent. It's like taking tiny, super cautious steps. It's really robust, but it can be pretty slow. A much more common approach is to use big chunks of data. That's batch gradient descent. It's a fantastic trade-off, giving us a great balance of speed and reliability. It's really the engine behind so much of modern machine learning.
And all of this, it brings us to one final, really deep question. After all this modeling, all this analysis, all this optimization, what have we really done? What part of any signal is actually predictable, and what part is just pure, untamable randomness?
Well, it turns out there's this absolutely mind-blowing piece of mathematics called the Wold decomposition theorem that gives us the answer. It reveals a fundamental truth about any stationary random signal. And stationary is just a fancy word for a signal whose basic personality, its average, its variance, doesn't change over time. It has a consistent character.
Okay, here's the incredible insight. Wold's theorem proves that any of these signals can be perfectly split into two totally separate parts. The first part is a predictable component, something deterministic, like a perfect sine wave. And the second part is a regular component, which is nothing but pure, fundamentally unpredictable noise. Every complex signal you've ever seen is just these two things mixed together.
So what does this all mean? It means that prediction isn't magic. It's not a crystal ball. The science of prediction is really about perfectly modeling that deterministic, predictable part of the signal, while at the same time learning how to recognize and filter out the purely random part that can never, ever be known ahead of time. Which leaves us with one last thing to think about. As our predictive algorithms get more and more powerful, are we really learning to see the future? Or are we just getting incredibly good at telling the difference between the signal and the noise?